The second part is to look at the East Asian early summer rainfall, not just southern China, but the entire East Asia. So this is, you have to predict the anomaly pattern. Now we are using so-called predictive mode analysis. Now, as I said, this East Asian MG climatology features, if we look at how the four dynamic model MME did on the rainfall climatology MJ, you see that is quite different, right? So you see this tropical rain band is over here, is far moved to the north. And originally there should be a rain band here. It becomes a dry band because the subtropical high location is wrong. And the rain band shift to march north. Okay? So this is how bad are our dynamic models. If you don't believe me, you should check every of your couple models to see how they produce East Asian summer monsoon, circulation system, and precipitation. Now, given such bias, you probably thought this model is able to capture interannual variability. Okay? So the interannual variability prediction scale for rainfall average over this entire region is 0.19. It's not very high. Okay? Some places has more prediction scale for the reasons, I think, okay, anyway, the question is how to predict the rainfall anomaly pattern. Now we are trying to predict rainfall anomaly everywhere in the East Asia domain, the monsoon domain. So the methodology we use is a predictive mode analysis called PMA, and use that to identify major pattern of summer rainfall anomaly. Okay? Then we use PE model to predict each of the principal component. And then we can reconstruct a prediction equations for rainfall anomaly. And we can also estimate the lower bounds of the predictability for this rainfall in the East Asian monsoon regions. Now, what is the predictive mode analysis? Now, this was proposed in 2007, and Junyi has done a series of study using this to look at the winter temperature predictions, the circulation anomaly predictions, and so on and so forth. It's essentially an approach to integrate the following 5 aspects of the climate study. First is detecting the most important patterns of variability. And this is like empirical study. And the second is to understand the source of the variability of those principal modes. Third, we need to establish PE model, prediction equations. And fourth, we should identify those predictor modes by either using handcast of dynamic model or use PE model. And the last, we can estimate the potential predictability. Because if we know which modes are predictable, we can assume the model, we can predict those predicted mode perfectly, then estimate a lower bound for the predictability. Now, therefore, we have to take empirical study for this region. The first UF mode, 27%, represent enhanced rainfall anomaly here and the dry anomaly there. This is the first UF mode. And corresponding to this mode, you see this is temporal variations. There is a sudden change around 93, 94. Okay, looks like two regimes. This is the so-called East Asia decadal variability in the middle 1990s, very clearly reflected in the UF1. And they are related to the equatorial SST anomalies. Is similar to the feature I showed, southern China is a rapid decay of El Nino, and there is a cooling, warming dipole over the equatorial region during winter time. Well, because the South China rainfall index is highly correlated with the UF1, therefore the predictors are also similar. Okay. Now UF1, I argue, often occur during unsolved decaying phase or rapid decaying phase. And the major feature is, again, this subtropical high anomalies, okay, and coupled with the cooling and the warming. The cooling is in front, the warming is behind. It's a huge system. So I still argue this positive feedback between the West Pacific subtropical high anomaly and the underlying Indo-Pacific warm pool SST dipole can maintain both the subtropical high and also the SST anomaly from winter to early summer. Okay. Now, therefore, one of the predictors is to look at, this dipole SST. Of course, you can also pick up the Eastern Pacific SST anomaly and then the North Atlantic tripole SST anomaly. Okay, and this one is a persistent signal, JFMA, 4-month mean SST and 2-meter air temperature anomaly. So those are persistent signals. And those are tendency signals, March, April mean minus January, February mean. Okay. Now you see the contrast, SST variability and land surface warming and the cooling over the East Asia or West North Pacific region. So there are 4 predictors are 1, 2, 3, 4. Okay. Now, this is a candidate, and this is only focused on the 0-month lead because we have to use March, April conditions, persistent signal and tendency signal. Okay. Now, basically, you're looking at the most significant signals as well. There are some signals over the southern hemisphere because it's far away from the East Asia regions. You don't think it's physically plausible. Right? So therefore, you can identify those predictors for the first UF mode. Okay? Now, which is this 3. This is the definition. Okay. Now, next, I want to introduce the other UF pattern to see whether we can get predictors for those UF pattern. So UF2, I argue, is mainly associated with North Pacific anomaly pattern. This is a simultaneous correlation with the PC2 of SST anomaly and the land surface 2-meter air temperature anomaly and wind. So you see the large anomalies over the North Pacific. It's like PDO-like SST anomalies. Okay? Now, of course, whether this is a major driver for this anomalous pattern, you have to show it, right? But at least it suggests that there is no other significant, for example, equatorial region, you see there is nothing, Okay, there is nothing. Well, there may be some development of the warming after the later part of the year, but not the precursors. So the largest signal is over there. Therefore, we are still looking at the persistent signals in the North Pacific. And there are some signals in the Southern Indian Ocean part. And if you look at the tendency signals, there is a warming in these regions. Okay? This warming is a major signal, significant signal related to this second UF. Now, there, so for the third UF, I think the main signal is the Equatorial Central Pacific cooling. This cooling starts from March, last to September. It's just a summertime cooling. And if this occurred, now this is the major signal corresponding to this complex pattern. And this pattern is really, it's hard to explain in details, but if there is a cooling in the Equatorial Central Pacific, you would think there is a suppressed convection over these regions. Okay. Now this suppressed rainfall, that regions may be related to this anticyclonic anomaly. This anticyclonic anomaly is small scale, just southeast of Japan, but it's quite important to produce this dry here. And to its north is a white. So there are a lot of rainfall probably around Jeju Island and the southern part of South Korea. So this mode could be locally important for this region, and especially to the eastern domain of the East Asian summer monsoon. So we have looked at the precursors, and again, there are two precursors has been found. One is for two persistent precursors. One is in the Central Pacific, another is over the land. Over the land is SLP. It's not the 2 meter temperature. SLP is the right contour, is high pressure. The entire Asian land is high pressure, persistent high pressure. But this is the important part, is very is right to the north of the East Asian monsoon regions. And there is also North Pacific signal. For the fourth UF, it is more difficult when you go to higher mode, because the frictional variance becomes smaller, and this like a east-west contrast pattern. But this contrast pattern has to do with strongly with this anticyclonic anomaly, and the anomaly center may be near Okinawa. Okay, this is very strong center there, and this is a dominant system to produce this east-west anomalous pattern. And in order to get predictors, you see there are many signals, but probably meaningful signal is those land surface tendency and persistent SLP anomalies in these regions. Later on, it maintains this anticyclonic circulation anomaly. But again, this becomes harder to explain why the warming here, cooling there, the tendency will eventually lead to this East Asian monsoon rainfall anomaly pattern. So now it's more like a statistical predictors. But again, this is only for persistent and tendency. Now the This one is even weaker, and the pattern is not very coherent, becomes more local scales. However, it does have some signature on the land surface warming, including Tibetan Plateau regions. So we could not find many predictors, probably only 2, but those has to do with land surface forcing anomaly. So that is a list of all 5 predictors. Now, the PC1 to PC5 can be predicted by this empirical model using those selected predictors. Now, the cross-validated scale is listed here. And this is a simulation scale. If you don't do cross-validation, it's slightly higher. If you do cross-validation, of course, is lower. But it suggests that those PCs are probably predictable to a large extent. Okay. Now, because of this, we can use spatial pattern, which is a function of longitude and latitude, observed rainfall pattern. And this PC, however, is predicted by those PE model. So we can use the first 5 mode to reconstruct the anomaly field. So you will eventually get May-June averaged anomaly field. Okay. Now these PCs are predicted using the persistent and tendency predictors in the lower boundary forcing. So this is the panel B is a cross-validated PE model hand-cast temporal correlation scale. In other words, for each grid point, you have 35-year time series. It's correlated with observation. So you can see the large prediction scale is in this part, not in those dry regions. Okay. Now the entire area average scale is about 0.4. Okay. Now suppose this 5 UF mode can be perfectly predicted. Then this should be the maximum, potentially maximum attainable scale. And this attainable scale for the entire region is about 0.60. So this can be viewed as a limit, because the higher mode, the UF6 and onward, is more patchy and more uncertain. So we think those are not predictable. Okay? So this is an estimation of the predictability, and this is the cross-validated scale. And this is a year-to-year fluctuation of the potential predictability and actually scale. Some of the years, scale is very low, because those years itself, this first 5 mode, does not capture much of the total frictional variance. Summarize, the May-June East Asia rainfall variability is primarily attributed to the following processes: positive feedback between anomalous West-North Pacific subtropical high and underlying Indo-Pacific warm pole ocean. The forcing associated with the PDO like SST anomaly, again, those need to be tested. Okay? And the development of Equatorial Central Pacific SST anomaly, a kind of a CP type La Nina, and maybe Tibetan Plateau and the Eurasian land temperature anomaly. Now this 5 UF mode seems mainly associated with those processes. And the major predictors are the persistent and tendency predictors in SST anomalies over the Pacific, especially the North Pacific and Equatorial Pacific, Indian Ocean and the North Atlantic Ocean, as well as land surface thermal anomaly over Eurasian continent. So a suite of PE models for prediction the first 5 PC basically has cross-validated scale of 0.5 to 0.8. Now, if we think those are predictor modes, okay, the MGI rainfall handcast over the East Asia, we can obtain the TCC scale over the domains of 0.4, which compared to the dynamic model is better. And the potential maximum attainable pattern correlation coefficient scale is probably around 0.6, not 0.75, I think. Yeah, this is like 0.6, so that's a mistake. Anyway, now I move to the last part, is a peak summer. In other words, July, August, East Asia monsoon rainfall prediction. This is the climatology of July, August. The major rain is moving to this part, and this is still the Indian monsoon trough, West Pacific monsoon trough rainfall. The subtropical high ridge is close to 27, 28 degrees during the July, August. The lower panel shows the 4 dynamic models predicting rainfall scale in the East Asia monsoon region. We call this the southern part of East Asia. This is northern part of East Asia monsoon. So area average scale is 0.19 and 0.13. So this part is more difficult than this part, obviously. And mainly dynamic model has a scale over Japan. So Japan is pretty lucky that their July-August rainfall prediction can be better. The other places are not very useful. Now, given this, again, we have to look at what is their major patterns. The UF1 is 25%, correspond to dry here, or the white there. And the climatological mean rain band is over this region. So this pattern is really represent advance of the Chama rainfall, not abnormally advanced, okay, compared to normal years. And the interannual variability is large and very irregular. Given this shape, you know how difficult to predict. But you see this 93, 94 is a large contrast in 2 years. We know in the 94, this Japan is very, very dry, and 93 was very white. So this pattern projects to this 93, 94 strongly. And also this pattern has a trend in the last 30 years. So it means there is a whitening, white trends in the northern China. Okay. And they are related to equatorial SST anomalies, but more like simultaneous. Winter time is weak. During summertime, looks like there is a development of the Western Pacific, very strong warming, and relatively cool. But this is statistically very significant. So in other words, this equatorial Western Pacific warming is a major characteristics of this. And I think this warming is important because it generates the but the enhanced convection band north of this warming region by create the low pressure. And then it's very similar to this so-called PJ pattern from Philippine Sea to suppress the rainfall over the Japan and East Asia monsoon regions. So in July, August, this rainfall pattern has very much to do with those West Equatorial Pacific. This is very different from our conventional thinking, because you may think July, August, the major pattern is still related to the ENSO, but actually it is not. It is not. This is not the ENSO years. This has nothing to do with ENSO, okay? But it has to do with very strong Equatorial Western Pacific SSE warming. So for simultaneous anomalies, when we see Equatorial Western Pacific strong warming, it is possible to excite this type of meridional tidal connection pattern to affect East Asia. So you see this rainfall anomalies very strong. To get persistent and tendency predictors, we have to look at the upper panel is persistent. This is March, April, May, June, 4-month mean SST anomaly, and this is SLP anomaly. Okay. I said we look at only two fields. And the tendency is MGL minus March, April for temperature and SLP. So you can identify many of the signals. For example, this Equatorial Western Pacific warming is a persistent signal. It's not just occurring in July, August, but it occurred well before this 4-month mean. Okay? Now you may want to take this as a predictor, of course. And then you can take sea level pressure dipole anomaly. Eastern Pacific is positive and this region is negative. So you can take 1, 2, and you can also notice the higher latitude sea level pressure drop and the sea level pressure rise. So this means there is a southerly flow in this region, and this southerly flow produce land surface temperature positive anomaly. So they are very consistent. So you can pick up this land-ocean thermal contrast in the previous 4 months as another predictor. For tendency, you may want to think about this SST cooling from March, April to May, June. And this SST cooling actually is favorable for setting up those Indian Ocean stronger monsoon. And also the South Asia low pressure tendency. This drop of pressure is favorable for South Asia monsoon stronger. But a stronger South Asia monsoon eventually can set up this wave train to affect the Northeast Asia part. So you can have 1, 2, 3, 4, and 5. But those predictors, we can use a stepwise regression to select because they are not independent of each other. If they are not independent of each other, we have only 35 years of data. We cannot use more than 3 predictors. Otherwise, it's overfitting. So therefore, we can use a stepwise regression to statistically select these 5 predictors. And then eventually you have only 3 left, okay? This is for the you have two patterns for this northern East Asia monsoon regions. Right? This is an anomaly pattern. It has little to do with winter warming, but it's not strongly related to the ENSO. Okay? Now, that means in this part of the world, ENSO impact in the July-August is not very strong. Okay? Now, probably the strong signals you can identify is that there is an enhanced CHAMA, important probably for Korea, and this enhanced CHAMA has to do with West Pacific subtropical high center in the Okinawa. Okay, this provide the moisture, and to the north is low pressure. That's why you have all this large area enhanced rainfall. Okay. It is circulation anomalies associated with that. And if you look at the sea level pressure, you see this high pressure system, this low pressure system. Okay. This creates this number 2 mode. Okay. Now, it also has a hint that this anticyclonic circulation anomaly to the front is relatively cool, and to within this anticyclone, because the subsidence SSC is warm, and to the rear part is also warming. Okay, there are some suggestions the local Earth interaction is important. The predictors, I don't want to go to much details, but you can find some significant signal in the persistence field and also the tendency field. It's only 3, okay, not many. For the third UF, it seems has to do with the Central Pacific ENSO anomalies. As you can see that by July, August, the Central Pacific is cooling, and it comes from a warming background, so rapidly transition to a Central Pacific. So the Central Pacific El Nino or La Nina, in this case it's a La Nina, it could have impact to this part, northern part of East Asia. And the characteristic rain band is this sandwich type of nearly east-west patterns. And those patterns are associated with the circulation anomalies. And the anomalous center is this anticyclone here. Center is probably in the north-south China Sea. And this anticyclone is elongated all the way to India. And to the north is cyclonic anomalies, very strong cyclonic anomalies over Japan. Okay. Now, the precursors, of course, we are focused on the Central Pacific La Nina. So you can see the 4-month persistent high pressure in the Equatorial Central Pacific is a big signal. Of course, you have some cooling already, cooling tendency, warming tendency. So you can pick up this cooling tendency, warming tendency, and the North Pacific signal sometimes linked to the Central Pacific SSC variability. So there is a tendency signal and also the persistent signals related to this Central Pacific cooling. The fourth UF is more difficult. It's more like this tripod type of dry white and dry pattern, and the corresponding anomalous Northeast Asia low. There is a low pressure system in this part. The Northeast Asia low system is a system affect East Asia summer monsoon, which has not been paid much attention to it. Recently, one of my friends in IEP, we specifically look at the Northeast Asian summer low. How does it affect the East Asian summer monsoon? But this fourth mode reflected very well in this low pressure system and the rainfall anomalies. Okay. Now to the source, you have a generally high pressure anticyclonic anomaly. The signals precursors mainly in the North Pacific and some of the overland regions. The land region, there is a warming here and a cooling there. The warming cooling is related to a barotropic anticyclone and a cyclone. Okay. Anticyclone is subsidence. They warm up the land surface. So this land surface actually reflects the wave train pattern. And those wave train pattern tendency, of course this tendency, how does that directly related to this Northeast Asian low is a matter of investigations. It's not very clear. So this summarizes this 4 PC and their corresponding predictors. And this figure shows the cross-validated scale for 0-month lead. Not very high, 0.6 something. Okay. So during the July-August, it is more difficult to predict those rainfall anomaly pattern. As we said, the first two basically is not ENSO related. This one is Central Pacific ENSO related. This one is more like wave train from Eurasia land come down to the Northeast Asia. But those mechanisms are less understood. So if we use these 4 modes as we think they are predictable mode, so the maximum attainable scale is again 0.6 over these regions. Okay. However, if we look at the 0-month lead, forecast scale is only 0.37, but it's not too bad in this region. And the difficulty is this dry regions. And this is a 1-month lead. The 1-month lead predictors are basically the same as 0-month lead, suggests that the selected predictors are quite robust. But when the lead time increased, the prediction scale reduced. Okay, anyway, let me summarize. For July-August, we identify 4 empirical orthogonal modes for July-August rainfall anomaly. One is Equatorial Western Pacific SSC anomaly related teleconnection pattern, meridional teleconnection. And the second is West Pacific subtropical high and the dipole SST feedback. The third one is the Central Pacific ENSO. And the fourth one may be related to the Eurasia wave train pattern. And you can see that what controls possibly the July-August variability in the northern part of East Asia has very little to do with ENSO, except this one. All others, you have to have very different thinking differently. And if you just based upon the ENSO prediction, you want to make a prediction of rainfall in these regions, is impossible. Okay? Now, we argue these 4 modes to some extent are predictable. Therefore, we can use them to do anomaly pattern predictions, cross-validated scale 0.37. But remember, the dynamic model is very low. So the potential attainable pattern correlation coefficient in the scale may be around 0.6. Okay. Now, okay, final transparency I want to discuss for all these three parts, for all this PMA method and the PE model method. Understanding the physical linkage between the predictors and the predictants is a key. And those represent advancement in the climate research. For many years so far, what we have been focused on is the simultaneous relationship. We want to understand how the lower boundary anomalies link to the simultaneous atmospheric circulation anomaly and rainfall anomaly. Okay? Now we have moved forward, not look at the simultaneous, but look at the predictor and the predictant. Those are lead-lag correlations. Those correlations are more difficult to understand. It is more challenge, and I think that we are facing a stage we should move away from just understand the simultaneous relationship. We should move forward to understand this lead-lag correlation. So the highlight the importance of those works is that we are trying to move forward. We are trying to establish a physical understanding of the lead-lag correlation. And you know how difficult it is, right? But we are trying to explain or propose hypothesis. I must see that the lead-lag relationship have identified in this study sometimes are not well understood, right? And we should treat those interpretation as a hypothesis. And those hypotheses should be tested by couple models. Of course, even use models to verify those hypotheses could be very difficult. But I emphasize that we should do this to enhance our understanding. Okay? Now, the third point I want to emphasize is those methods is not just to provide the predictions, but also can help identify dynamic models problems. The current dynamic models I didn't show, but they have a difficult to capture UF2 to UF5. So for MJ, we identify 5 UF. For JA, we identify 4 UF. Now, except the first UF, dynamic model has a skill to capture them. The other UFs, the dynamic model has a tremendous difficulty. So we should understand why the models cannot capture those modes. Now, we identify they have serious climatology bias in that regions. And they also have the deficiencies to describe atmospheric response to SSE anomaly outside of the Equatorial Pacific. So those are more difficult. I think also capture the atmosphere-ocean interaction and atmosphere-land interaction. The impact of the land surface anomaly is not very good, and we do not understand very well. The fourth point I want to discuss is long lead forecast versus short lead forecast. Long lead forecast is desirable, okay, compared to short lead. The short lead, when I talk about the MJ rainfall anomaly pattern and the JA rainfall anomaly pattern, are all short lead, either 0 month or 1 month. Because those persistence predictors and the tendency predictors are easier to understand. If you go further earlier, it's more difficult. So therefore, the PE model is probably more suitable for short lead. But occasionally, you can find a long lead, like South China rainfall. Now for MJ, UF1, you can have this long lead forecast, 2-month lead. But for other 4 UFs, you cannot find this long lead predictors. That is why when we predict the rainfall anomaly pattern, we go to the short lead. Now the short lead means that for July-August prediction, you have to watch your May-June. So that you have to realize that if you want to do July-August predictions 2 months earlier in spring, I'm not saying it's impossible, but it's extremely difficult in terms of this research. This research tells you that you can look for those, but physical interpretation will be extremely difficult. You can do pure statistical model. Okay, so this long lead versus short lead, you have to link to this PE models and understanding of this lead-lag relationship. This is another important thing. We should consider the secular change in the predictors. All we used here is 34 years of data. This is not long enough. And the predictors we have been confirmed or identified could be changed in the future. So we have to be very alert on this. And tomorrow I'm going to go to PNU to have another talk about the Indian summer monsoon predictability. Indian summer monsoon has 140 years of data. So therefore, I can talk about the secular change. Almost no predictors are valid across 140 years. They all have multi-decadal variability. Okay? Even their relationship with UNSO, physically a very solid relationship, they are changing with time. So we have to be very, very cautious about the predictors derived from this 35 years period. So we have to keep in mind they can change in the future. So you have to watch every year. Another caution is this cross-validation is not a rigorous verification. The skills, the cross-validation skill, I think still have inflation. Okay? In other words, the actually prediction skill will still drop. Okay? Now the reason is because the cross-validation is not independent validation. So you take 3 years out, you use the data before 3 years and after 3 years. You use the data in the past and the future. So that gives you the benefit. Your prediction is better. Now, in the Indian monsoon situations, we have tried independent forecasts. In other words, we use data only before the forecast date. For example, 50 years before. From 1871 to 1920, 50-year data. We build the equations. Then forecast another 10 years. Then we move forward using 50 years, make another 10 years forecast. So we made 92 years so-called independent forecast. You see the independent forecast scale is lower than this cross-validating because it does not use the information in the future. Now the most rigorous test, of course, is the independent forecast. If you have 140 years of data, you use 100 years data to establish equation to look at the 40 years as an independent test. In that case, you would find the scale is even lower. But anyway, there are many issues related to this type of research. But I hope that my talk will be useful for you to think about this problem. Again, rainfall prediction is the most important and is most difficult. And we have to face it. So I would be happy that those prediction tools actually transfer to APCC. Besides your multi-model ensemble forecast, you can have another set of products which using, for example, PE model. You test in the operational science. So we are going to make those available.